Hey class! Today we're going to continue on with section 2 about electron arrangement of atoms, and we're going to fill out the second part of your guys' homework worksheet talking about noble gas notation. So let's do a little recap of what electron configurations are. The way in which electrons are arranged or placed in different orbitals around the nucleus of an atom is called an electron configuration. Again, it's usually represented by a number followed by a letter and then a superscript. The number in front represents the energy level. So this could be energy level 1, 2, 3, 4, all the way up to 7. The letter is going to represent the type of orbital. So we talked about 4 different types, S, P, D, and F. And then our superscript up here is going to be the number of electrons that are in that orbital. Specifically, we learned that S's can hold a maximum of 2 electrons, P's can hold up to 6, D's can hold 10, and F's can hold 14. We also did an example in our notes, and the last one we did was gallium, which has the atomic number of 31, which means it also has 31 electrons. And we have in our notes that the electron configuration for gallium is as follows: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p1. One thing to also kind of review is these superscripts, the 2, the 2, the 6, 2, 6, 2, 10, and 1, all add up to this 31. Now, sometimes writing these configurations can get very long. For example, on your guys' homework the other night, you guys had to write iodine, which is very, very, very long. So we need to find a shorthand way to write electron configurations, and that's where we're going to learn noble gas notations. Before we can talk about noble gas notations, we first have to understand what is a noble gas. Noble gases are the elements located on the far right-hand side of the periodic table. People often say that this belongs in group 8A if it's going by the US system of naming, or group 18 if we're going by the international system of naming. Elements in this group include helium, neon, argon, krypton, xenon, and radon. To give you a little bit of visualization, here is your group number 18. Again, this is sometimes referred to as 8A. Again, the elements are helium, neon, argon, krypton, xenon, radon, and then oxygen or something like that. Again, these are the noble gases. So how do I take those noble gases and write something called a noble gas notation? Well, first we have to understand what exactly is a noble gas notation. A noble gas notation uses noble gas symbols, and we place them in brackets to help shorten our inner electron configurations of our elements. So we're taking those electrons that are on the inside energy levels and putting them in a form that is shorter. Typically, this leaves your valence electrons that you have to write. So the steps in order to do a noble gas notation is as follows. 1. Determine the noble gas that comes before the element. There are 2 key things about this. 1, it has to be a noble gas that goes in brackets. That means it has to be either helium, neon, argon, krypton, or radon. It cannot be any other element but those ones. The other key word is it has to come before the element. Second, once you know what noble gas it is, you're going to place it in brackets. When you place noble gases in brackets for electron configurations, they represent the number of electrons for that noble gas. For example, argon, since its atomic number is 18, it will represent 18 electrons. If you put neon in brackets, neon would represent 10 electrons because its atomic number is 10. Third, you're going to substitute this bracketed noble gas in for the same number of electrons in the configuration, and then you're going to write whatever is left. So let's look at the example of sodium. Sodium's element symbol is Na, and its atomic number is 11. If we were to write out the complete electron configuration, we would write it out as 1s2, 2s2, 2p6, and 3s1. However, In order to write it into the noble gas notation, you're going to have to look to see what noble gas is less than 11. It cannot be greater than 11. So we're going to look back here, and the closest noble gas to 11 that doesn't go over is actually neon right here as 10. So what you would do was you would put neon in brackets. Now neon represents 10. So that means when I'm looking at this, these first 10 electrons are being represented by Ne. So 2, 4, 4 plus 6 gives me 10. This first part is neon. That means I only have to write what's left. So here you're going to notice that 3s1 is written after it. Now we're going to do a practice of writing the noble gas notation for phosphorus. Now remember, phosphorus is P, and phosphorus's atomic number is 15, so that means it has 15 electrons that we are working with. If you were going to do this, we would have to look to see which noble gas is less than 15 and it can't go over. So which noble gas is closest to 15 without going over? So if you look over here, the closest is 18 or 10. Well, 18 goes over 15, so it cannot be argon, and notice the closest one without going over is neon again. So we're going to place neon in brackets. Now neon represents 10 electrons, but I need to get to 15, so we have to keep going. If you're actually looking at this chart that I gave you in class, I had people get out this chart and actually write down the noble gases atomic number. So I had them write 2 here, 10, 18 in this box, 36, 54, and 86. I told them this was fine. You can write this on your thing. You can use it for your test because it does come in handy. In fact, I told them if they wanted to write the atomic number of all of these elements, they could have. So if you wanted to put 1 here, 3, 4, 5, 6, you're fine doing that. Now the reason I had them put that is because if neon stands for 10 electrons, my electron configuration is going to have to take place after the number 10. So if I'm looking here at 10, if I need to keep going to 15, I need to keep going from 2p. After 2p is 3s. So I'm going to write up here 3s, and it can hold 2 electrons. So now I have 10 electrons plus 2 and gives me 12. I still haven't got to 15. So we need to see what's after 3s. So after 3s, if you're reading it like a book, you would have 3p. Now P can hold up to 6 electrons, but if I put the number 6 here, it would put me over 15 electrons. I've already used 12, I only have 3 left to give. So this is going to be 3p3. So this would be your final answer. Now there are some exceptions to the electron configuration. They do not follow Aufbau's principle, which, if we remember correctly, Aufbau's principle states that you must fill lower energy levels first before you move to the next energy level. And there are 2 elements that kind of are known best for not following this rule. And those 2 elements are chromium and copper. Now they are not the only ones, but they're the only 2 that you see regularly. If we were actually following Aufbau's principle, you would write chromium and copper as such. And when you do that, this is actually going to be incorrect. So instead, they violate Aufbau's principle, and if we were to write them like they should be written, this is the correct version we get. One thing that you should notice between the correct and incorrect versions has to do with this last little part. This used to be 4s2, 3d4. And what they essentially did was they took one of the electrons out of s and they gave it over here to d in order to make it have 5. Same thing happened with copper. They took an electron out of this s and gave it to d in order to make it 10. The reason they did that was to make this orbital half filled instead of just 4. And they did this one to make this orbital completely filled. And one thing I will tell you is it all comes down to stability. It is more stable to have this d orbital half filled than it is to have the s completely filled. Same thing for copper. It is more stable to have the d completely filled instead of having the s completely filled. So when I ask you why do some things violate the Aufbau's principle, some electron configurations actually differ from those that we assign them based on the Aufbau principle rule, because while half-filled sublevels are not as stable as filled ones, these configurations tend to be more stable than other ones. So the whole reason some elements violate Aufbau's principle has to do with stability. This is the key word. We want atoms to be as stable as possible. That way we don't get things like nuclear reaction spills. So it all comes down, again, to stability. If you have any questions, please let me know. Otherwise, that is the end of your lesson, and I hope you guys have a great day.